Hello everybody, welcome to our next video. We left off at this point that we had to start general transformer architecture. So basically what transformer does is we know, and its architecture is composed of two things, encoder and decoder. So encoder will receive the inputs and it will build some representation of it, like the features, and then the model is optimized to acquire the understanding from the input, and then decoder uses that representation of the encoder, that is the features, along with some other inputs, and then generates a sequence, that is the target sequence. So that is called a transformer. So we know what transformers are. The transformers are used to like solve all kind of tasks, and the transformer library had a function called pipeline. And if we just go to here from transformers library, we had to import this pipeline function and create an object, and then just we can just get those answers. Now going further, like here, so each of these paths can be used independently depending on the tasks. So we have like encoder only models which are good for tasks that require understanding of the input. Okay, and the decoder only models which are for generative tasks. Okay, and encoder decoder models which are for generative tasks which requires an input, and then like such as translation and summarization. A key feature of transformer models is that they are built with special layers called attention layers. Okay. In fact, the title of the paper introducing the transformer architecture was this: attention is all you need. Yeah, we will explore the details of attention layers. So, transformer architectures are built with some layers called as attention layers. All you need to know is that this layer will tell the model to pay specific attention to some words in the sentence that you passed it. Okay, and more or less ignore the others. Okay, so attention just tells the model the model that you have to pay attention to only these words and you can ignore the rest when dealing with the representation of each word. To put this into context, consider the task of translating English from English to French. You like this course. A translation model will need to also attend to the adjacent word you to get the proper translation for the word like, because in French the verb like is conjugated differently depending on the subject. The rest of the sentence, however, is not useful for the translation of that word. Yeah, so in the same vein, when translating this, the model will also need to pay some attention to the course, because this translates differently depending on whether the noun is masculine or feminine. Again, the other word will not matter for the translation, of course. So with more complex sentences, the model has to pay attention to specific words that might appear farther away in the sentence to properly translate each word. Okay. Rest, like if we know what are transformers models. So it is a foundational deep learning architecture that powers modern generative AI. Unlike older models that process words sequentially, transformers keeps entire sequence simultaneously and track relationships and content using a math called as self-attention. So this is built on like a few components which have like encoder and decoder architecture as well. Yeah, we are here. The same concept applies to any task associated with natural language, that a word by itself has a meaning, but that meaning is deeply affected by the context, which can be any word before or after the word being studied. Now that you have an idea of what attention layers are all about, let's take a look at the transformer architecture. This was originally designed for translation. During training, the encoder receives some inputs in a certain language, while decoder will receive those same sentences in the desired target language. So in encoder, the attention layer can use all those words in a sentence. As we just saw, the translation of a given word can be dependent on what is after and as well as before. The decoder works sequentially and can only pay attention to the words in the sentence that it has already translated. So only the words before the word currently being generated. For example, when we have predicted the first three words of the translated target, we give them to the decoder, which then uses all the inputs of the encoder to try to predict the fourth word. To speed up during the training, when the model has access to the target sentences, decoder is felt fed the whole target, but it is not limited to use future words. If it had access to the word at position 2 when trying to predict the word at position 2, the problem would not be very hard. For example, when trying to predict the fourth word, the attention layer will only have access to the words in position 1 to 3. Yeah. While with the decoder on the right and encoder on the left. So attention, addition and normalization, feed forward, and this is output. Note that the first attention layer in the decoder block pays attention to all the past decoder blocks. But the second attention layer uses the output of the encoder. First just passed, and then the second uses the output of the encoder. It can thus hold input sequence, very useful as different languages can have grammatical rules. The attention mask can also be used in this to prevent the model from paying attention to some special words. Next is architectures versus checkpoints. As we dive into transformer models, you'll see mentions of architectures and checkpoints as well as some models. These terms all have different meanings. So architecture is the skeleton of the model, like the definition of each layer and each operation that happens within the model. Okay. Checkpoints are the weights that will be loaded in a given architecture. Okay, the weights that are loaded in that architecture. Architecture is the skeleton and the model is the umbrella term, which is not precise as architecture or checkpoint. It can mean both. So BERT is an architecture, while BERT base case is the set of weights that is trained by Google team for the release of BERT, which is a checkpoint. However, one can say the BERT model or like this model. Okay, checkpoints are the weight, but architecture is the skeleton. Next, how transformer solves tasks. So in transformers, what can they do? We learned about NLP, speech and audio, computer vision tasks, and some important applications of them. Now this page will look closely at how models solve these tasks and explain what's happening under the hood. There are many ways to solve a given task. Some models may implement certain techniques or even approach the task from a new angle, but for transformer models, the general idea is the same. Owing to its flexible architecture, most models are a variant of encoder-decoder and encoder-decoder architecture. Okay. To explain how tasks are solved before diving, it's helpful to understand most tasks follow a similar pattern. Input is processed through a model, output is interpreted for a specific task. Differences is how data is prepared, what model architecture is used, and how the output is processed. Yeah. To explain how tasks are solved, we'll walk through what goes on inside the model to output useful predictions. We'll cover the following models and their corresponding tasks. So this is a model for audio classification and automatic speech recognition. This is for image classification. This is for object detection. This is for image segmentation. This is for depth estimation, NLP tasks like this, and for NLP tasks like this. Basic knowledge of original architecture encoder will aid you in understanding this. So be sure to check out previous done. Transformer models for language. Language models are the heart of modern NLP. They're designed to understand and generate human languages by just learning some statistical patterns and relationships between words or tokens in the text. Now, the transformer was initially designed for machine translation, and since then, it has become the default architecture for solving every AI task. Some tasks lend themselves to the transformer encoder architecture, while others are better suited for the decoder. And then still our tasks make use of both the transformer encoder-decoder architecture. Now, how language models work? They work by being trained to predict the probability of a word given some surrounding words. Yeah. This gives them an understanding of the language, and then they can generalize better to some other tasks. Now, there are two main approaches for training a transformer model. One is masked language modeling, that is MLM, used by encoder models like BERT. This randomly masks some tokens and then trains the model to predict the original tokens based on the surrounding context to learn some bidirection, looking at words both before and after. This is used by decoder models. GPT is a decoder model. This approach predicts the next token based on all the previous tokens in the sequence. So they can use context from the left to predict the next token. But this is like they can use context from the left and right and they just predict the middle word. That's mass language modeling. Types of language models. In the Transformers library, language models generally fall into three architectural categories. One is encoder only, decoder only, and then both encoder and decoder. Encoder only is that uses bidirectional approach to understand context from both directions. They are suited for tasks that requires deep understanding of the text. Okay. Decoder only models are like GPT and Llama, which processes text from left to right, and then they're good at text generation tasks like writing or like generating code. Then encoder decoder models are that combine both, uses an encoder to understand and then decoder to generate. They excel at sequence to sequence tasks like translation, summarization, and then question answering. Got it? And then, as we covered in the previous section, they are typically pre-trained on large amount of text data in a self-supervised manner, like without any annotations, and then they're just fine-tuned on some specific tasks. This is known as transfer learning, allowing the models to adapt to many different tasks with relatively small amount of task-specific data. Some model architectures and then how they are applied to various tasks across speech, vision, and text domains. Understanding which part of the transformer is best suited for a particular NLP is key to choosing the right model. Generally, tasks require bidirectional context use decoders, task generating text use decoders, and then, text generation. This involves creating coherent and contextually relevant text based on a prompt or input. Okay. So based on a prompt or input, we are just generating some coherent and contextually relevant text, right? GPT-2 is a decoder-only model which is pre-trained on a large amount of data, which can generate some convincing, always not true, but good text given a prompt and complete other tasks like question and answering. So text prediction and text classification. So how it works is this is the whole like next thing we will cover this in next video from here. So we'll cover in the next video from text generation. Let me just see what are the indexes using transformers and then fine tuning, sharing models, the datasets library, the tokenizers. Yep, we'll do this in the next video. Thank you for watching. Bye. Take care.